The problem Chyp has is to redesign their production line because they're going to launch a new product. They manufacture amplifiers, they assemble them, starting from raw materials and obtaining at the very end of the production line amplifiers. This is finished goods. So in this case, what they have right now, it's 4 stations, station 1, 2, 3, and 4. This S stands for 4 in this case. And they have to assign tasks to different stations. So for Chyp to obtain an amplifier, they have to perform all these 12 tasks. And they have a given time. So for example, installing or assembling the protective grid takes 13 minutes. And the same goes for the rest of the tasks. And for every task, you have some precedences. So you cannot, for example, use a task 6, which is connecting the printed circuit boards, which has precedences 2 and 3. So for you to connect the boards, you have to install them first. So that's why you cannot just assign tasks to station without disregarding those precedences. So the problem consists in deciding what to do in each station so that the cycle time is minimized and we satisfy all precedence constraints. The cycle time is the time in between 2 amplifiers coming out of the line, and the lower the cycle time, the more production we obtain from this line and the more money obviously we can get. What we did in the optimization approach, the deterministic approach, is to assume that all the process times were deterministic. So in the previous table, we knew for sure what was the time for us to perform every task. So we had a mathematical model, which is the one we have here. And for that, we had a software implementation. So every time we clicked this button solve, we obtained an assignment, and that was the design for our line, so that we knew what we have to perform in every single station. We saw some numbers, like for example, if we assign tasks 1, 2, 3, 5 to station 1, the time for us to perform all these 4 tasks was 3, 6, 7, and 4, so I know it's 20. If we assign to station 2 tasks 6 and 7, we'll have 17 minutes for performing all 3 tasks. All these 2 tasks, sorry. And if we assign tasks 4, 8, 9 to station 3, we have a time which is 19, which is 6 plus 11 plus 2. And finally, we have 20 minutes finally for station 4 because we assigned tasks 10, 11, and 12. This was the optimal solution we obtained when using an optimization approach, assuming that these times were always fixed once we pick a task. So in this case, we can estimate the resource utilization. So if we have this configuration of our line, we expect a cycle time of 20 because this lowest station is the one that sets the pace for the whole line. So these 2 stations, 1 and 4, are the slowest, and that means we're going to produce 1 amplifier every 20 minutes. So that is the cycle time, and since we're producing 1 amplifier every 20 minutes, that means station 1 is busy all the time. It's 1% busy because every time it finishes with an amplifier, it starts working on another one right away. But station 2 only works 17 minutes out of every 20, so that means that it's busy 17 minutes out of every 20, which is 85% occupation for this station. We can do the same math for station 3, so we expect 95% busy time for this station, and finally we expect station 4 to be busy 100% of the time because it's working 20 minutes out of 10 all day long, or during all the time the production line is working.